Okay, it looks like we're going good. I accidentally hit the wrong button. Okay, so let's look at the um, conceptual problems that we have here before us, and I'm going to let some of you um, log in and give me some answers. I want to try to get you a little bit more involved than say what we have been. Okay? So let's look at this first question. Hopefully everyone can see this okay. Basic kinematics, variables. The motion of a particle is described in the velocity versus time graph shown in the figure. We can say that its speed would be what? So if we look at this velocity versus time graph, if we look at this velocity versus time graph, what could we say about the object's speed? Okay. So does anyone want to take a stab at this?
It's constantly increasing.
Okay, so it's constantly increasing. Is that what you said?
Yes, I can't really see the answer choices.
Okay, yeah. You have the A increases, B decreases, C increases, then decreases, D decreases, and then increases. Okay, all right, so we have one that says it's constantly increasing. Of course, that's not one of the answers. Well, it does, yeah, increases. Okay, so we can go with that. Anyone else want to take a stab at it?
Decreases and increases.
Decreases, then increases. Okay, anyone else? Okay. All right, well, let's analyze it. Let's just analyze it before we decide on which answer is the correct answer. All right, notice this is velocity, and this is time, and of course velocity is in meters per second. Notice over here your velocity is negative, looks like it's about negative 2.5 when it starts out. All right, if we go up to 2 seconds, what would the velocity be? Well, it looks like at 2 seconds the velocity would be what? -1, right? Okay. So is the velocity increasing or is the velocity decreasing? It would be what?
Increasing.
All right. Well, if we're going from all right, but now I know you got to remember now. Let me reemphasize something here. The negative stands for the direction. Okay. The negative sign tells us the direction. So remember that. I know that it's getting, would everyone agree that it is getting more positive? Does everyone agree to that? That it is moving towards more positive?
Yes.
Okay. But you've got to understand something, that the negative sign represents direction. Okay? It doesn't have anything to do with the magnitude, the actual value, the actual quantity. It's just a direction. That's all the negative sign tells us. So, that being said, velocity, if it's 2.5 at 0 and it's 1 at 2 seconds, then that would tell me the velocity is decreasing, correct?
Yes.
In other words, the object is moving in the negative direction, but it's doing what? It is speeding up or slowing down?
Slowing down.
Very good, slowing down, okay? Now, so then if that's the case, our best answer would be D. It's decreasing and then increasing, because look, when we hit this position right here, what has happened right there? What has happened to the object right there where I put that red dot, where my arrow is?
It stopped momentarily.
Very good. It stopped momentarily, just a real, and then turned around. Then we start increasing in the positive direction. So in other words, the object was doing this. It was moving in the negative x, let's just say, hang on a minute. All right. So it's It's moving in the negative x, moving it slow and slow and slow and slow and slow and stop, and then it turns around and does this right here. Okay? Okay, and that's what it would look like if you were to plot it on an x, y, and we're just looking at, you know, x direction being the direction of motion. We're just assuming it's moving in the positive x. Okay? So that's how the object would actually appear to be moving. And of course, when it gets to what, 3.5 seconds, it's 3.6 seconds, 3.75. It stops momentarily. Okay, good. So remember that. Hopefully you remember that just because it's negative, okay, you got to understand the negative tells us the direction. Okay. All right, good. That's good. Now hopefully that'll shed some light. Now let's go ahead and look at this next one. And by the way, I pulled these off of my yeah, I'm sorry. Y'all don't let me overlook you if you raise your hand. Like I said, you can chime in. Does someone have a question?
I do. This doesn't have to do anything with what we're talking about right now, but what's the closest you can reach to a frictionless surface? Like, is it possible to have a surface with absolutely no friction?
You can get it pretty close. Ice, for example, if you're on ice, that is really, really close to being almost no friction. When you lubricate something, when you put oil on something, you really, really get the friction really low. I don't think we can ever say that it's completely frictionless. I mean, even if an object's moving through air, the only way it would be completely frictionless if it was in a vacuum. And there was nothing in that vacuum. I mean, it was just a pure vacuum. Then you would be completely frictionless. Does that make sense?
Yeah.
Okay. But you can get that friction down really, 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 really low. And that's the whole purpose of lubrication in an engine. You know, you don't completely, because look, if you completely did away with all the friction, then the engine would never wear out. I mean, is it possible to build an engine that would never wear out? Well, they can build them to go a lot farther than they do now. I mean, that goes without saying. You know, used to, these old engines would run a long time because they engineered them better and the materials they used were better. And two, they used leaded gasoline. And when they did away with leaded gasoline, the engines quit lasting as long, and they got to studying it, and they figured out that after you run the lead gas through an engine, it coats the valves. It puts a little lead coating on the valves, which really lowers the friction. So that's a good question, okay? All right, let's look at this next one. All right. Basic kinematic variables. Let's look at the motion of the car and the truck and along a straight road are represented by the velocity time graphs in the future. The two vehicles are initially alongside each other at time t is equal to 0. So they start at time 0. At time t, in other words, at this final point in time, they decided to pick this point here, right here, at time t. And it doesn't matter what the value of the time is. It's just that point. What is true about these two vehicles since time 0? All right, now notice, and again, if you can't see it, that is the velocity, and this is the time in seconds. All right, so what would we say when we start at time 0? What is the velocity of the car at time 0? Someone chime in. Anybody?
0.
Very good. It's 0 meters per second. It sure is. What is the velocity of the truck at time 0? And let's just say this is, let's just say this would be 1 meter per second. This would be 2 meters per second. That would be 3 meters per second, and so on. So at time 0, the velocity of the truck is what?
2 meters per second.
2 meters per second. Very good. And I just made those numbers up. It doesn't matter. Okay. Now, we know at this time interval, the truck is moving at what? What kind of velocity does the truck have, someone?
Constant.
Constant, absolutely. Very good. All right, so it has constant velocity. It has constant velocity. The car, however, its velocity is doing what over the time interval?
Increasing.
Increasing, absolutely. So which one of these will travel farther at time t?
The truck.
Very good, the truck. Because the truck has a constant velocity. Let's just say this time interval is 5 seconds. Okay. Well, 2 meters per second times 5 seconds, the average velocity is 2 meters per second because it's constant. Well, the distance would be what? Well, we know that the velocity average is equal to what? The change in displacement over the change in time. And so the change in displacement is equal to what? 2 meters per second times what? 5 seconds. So we've got what? 10 meters. It will have traveled 10 meters. Whereas the car is going to have an average velocity of 1 meter per second, because if you take the final and the initial, 2 minus 0, 2 minus 0 is 0, and then, let's see here, to do that right, let's see, 5 seconds, yeah, we got to find the average speed here, so it starts at 0, and 2 divided by 2 is what, 1? Yeah. So we would have 1 meter per second, so it traveled 5 meters. Okay, see how I did that? So you'd have to find the average right here, okay? So it's traveled half the distance, presumably. Okay, and again, that's all based on what these numbers are, and I just made some numbers up, okay? But it would still be less than. All right, good. All right, good. Okay, let's look at the next one if you don't have any questions about that. Oh yeah, I don't have to do that. I can do this right here. There we go. All right, let's look at this one. Basic kinematics variables. The graph in the figure shows the position of an object as a function of time. The letters, that's kind of hard to read, isn't it? Well, let me just look at I've got it printed off here. Yeah, that's a typo. That's an H. H through L represent particular moments of time. At which moments shown, H, I, etc., is the speed of the object the greatest, okay? So where would the speed of the object be the greatest? Now look very closely.
Point I.
Okay, point, that's actually 0. That's
Okay.
all right, point, did someone say H?
Yeah.
All right, let's look at H. Oops, I got to remember to turn my marker on. All right, someone said H. Any others? Now, I want you to be looking at something. Look at the steepness of that line there, and look at the steepness of the line there. Okay. So someone said point H. Anyone else want to take a stab at it?
J.
All right, point J. So we've got H and J. All right, well, let's look at it. Let's analyze it. Now, I know we don't have any numbers other than 0, and this is positive, and that's negative. But that really doesn't matter as far as, just interpreting what the graph's telling us. Notice the steepness of the line here. Notice that the change is over a shorter time interval. Notice from here to here is a shorter time interval than from 0 to here. This is a shorter time interval. So my velocity would actually be highest right here at J. Well, I say not the whole thing, but at J. So J answer is correct, okay? If you look at that and you say, why, Mr. Shields? Because the steepness of the line. You have a shorter time interval between those right there, okay? It's much steeper. There's a greater change. Now, yes, it would also be what? Would it be positive or negative? If I took the slope of this line right here, what would it be? Positive or negative?
Negative.
Very good, it'd be negative. So it would be negative, but it would be a greater negative. It would be a higher negative, It would be a higher number. Here, it's going slower. It's taking longer to get to the peak. So your time interval's longer, and when you do the average velocity, you see that it would be a lower number. Okay, does that make sense? I hope that makes sense. Look at your line. Look at the, okay, good, very good. Look at the steepness of your line. All right, now I know some of you are thinking, this is mathematics. Yeah, it's physics too, y'all. Because you're taking graphical, you're taking graphs, you're taking an object that its motion has been graphed, and then you're interpreting what's going on with the physics, okay? All right. Where would it be zero? Where would the velocity be zero?
Point I.
Point I, very good. So we said the greatest would be at point J. Greatest would be at point J. The least would be at point H. And then zero velocity, 0 meters per second, would be point I. Very good. Very good. Because it flattens. See, right there it flattens out. There's no change in displacement. And at that moment in time, it's zero. And what would its motion be doing? All right, let's draw it. I'm going to really analyze the fire out of these. All right, which direction is it moving right here? Which direction is it moving here, positive or negative?
Positive.
Positive. So it'd be going like this, wouldn't it? Let's just say this is X and that's Y. And then when it gets right here, what does it do? It stops and then does what? Real quick, doesn't it? Goes in the negative direction. Actually, though, I probably shouldn't have crossed the y-axis. I probably should have just stopped like somewhere right in here. Because when you get into a negative minus a negative, then it becomes positive. Okay, so you got to watch that. Okay? All right. But again, the positive and negative tells us direction. All right, good. I hope that helps. All right, let's look at the next one. I kind of need to move on here because I do want to look at some problems if we can. All right, here's another good one. Basic kinematic variables. A figure shows the graph of a position x as a function of time for an object moving in a straight line. Which of the following graphs best describes the velocity along the x-axis as a function of time for this object? So look at the different, and notice that you've got 5 graphs to choose from. I love this kind of stuff because this really helps you to understand. I mean, it's one thing to be able to take a calculator and calculate something, but it's another thing to be able to physically understand what's going on. All right, so notice it. So if we were to take this motion right here, that's a parabola, isn't it? And then we were to take this right here and then graph it. Which one of these would be correct? Did someone say D? This one? Okay, I think someone said D, did they not? Because what's happening here? You are getting what? Less and less negative, aren't you?
Yes.
All right, and then you become positive. But what's happening right here? What's happening right here? It's starting to do what? Flatten out. So the displacement's doing what? Becoming constant. And if the displacement is becoming constant, what's happening to the velocity?
Constant.
Well,
Well,
if you have no change in displacement, do you have any velocity? In other words, if you're traveling along and your displacement, you see what I'm saying?
yes.
Okay, so you've stopped displacing. So your velocity should be going close to 0, right? So D is correct. This is the correct answer. Okay? It couldn't be this one, because notice you have gotten, because see, look, what is it doing here? It's going in the positive direction. Okay? It's moving in the positive direction. it stopped here. So you're telling me here if you chose this one, everything is negative. No, it's not. No, it's not. Okay, so it would be D. That one there makes you really want to scratch your head a little bit. Okay, that's a good one. Any questions? Oh, did I go too far? I think I did. This pen is real sensitive. You don't hit it in just the right spot. Let me try it one more time. There we go. All right, here's another. I'm sorry, y'all. It's hesitating on me. There's a pause. Now, all right, the basic kinematics variable. An object starts its motion with a constant velocity of 2 meters per second toward the east. After 3 seconds, the object stops. The object stops for 1 second. The object then moves towards the west, a distance of 2 meters in 3 seconds. The object continues traveling in the same direction but increases its speed by 1 meter per second for the next 2 seconds. Which graph below would represent the motion of the object? Wow. Now there's a lot involved in this one. There's a lot involved. So you're doing what? Now notice we have plotted, this is all displacement. This is all x versus time, x versus time, x versus time. Okay, so we're looking at the displacement, okay? So it does what? It travels with a constant velocity. Ding, 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 ding. If you were to plot that on a distance versus time graph, what would it look like? If you were to come in here and say, okay, distance versus time. This is x and this is time. Displacement versus time. What would that look like? Would it look like that? It says constant velocity, right? If I were to take the slope of that line along any point along that line, would it get the same answer? Anyone?
Yes.
Yes, you would. Very good. Okay. So that's what constant would look like. Now, what would it look like on a I know I'm throwing something else at you. What would it look like on a velocity versus time, that segment? It would be what? That?
Straight line.
Very good. A flat horizontal line. Very good. Very good. Okay. So analyze that. Look at that again. Then it goes towards the east, and then after 3 seconds, the object stops for 1 second, so there's no displacement. And then it does what? Moves towards the west, a distance of 2 meters in 3 seconds. So when it stops, it's no longer displacing. So what should that look like on a graph, on a distance versus time graph? Displacement versus time. Should be a flat line, shouldn't it? A horizontal line? Okay. All right, does anyone want to go ahead and take a shot at which one of these 4 it would be, A, B, C, or D?
E.
D.
D.
D? I think most of you are saying D because we have 4 choices. Very good. It would be D. Yes, it would. Look, there's your constant velocity. There's your stop for 1 second. Notice it says it goes what? It reverses direction. In other words, the slope of that line is going to be negative because final is less than initial. So you get a negative, which means you've changed direction. Okay? Continues moving and increases its speed by 1 meter per second. So there's your increase. Okay? Okay? Very good. Very good. Now, see, you should be able now to take a graph and say, all right, what is physically happening with this graph? In other words, in the real world, what would my motion look like? And then you should be able to draw it. You should be able to say, well, it's going this way, and then it turns around and goes this way. You should be able to do that. And again, that's the whole purpose of this, conceptually, to get you to understand what is going on in the physical world. I know you're good with numbers. I know every one of you in this class is probably really good with numbers, and that's great, and that'll help you. But you've got to be able to put it into real life situations. You've got to be able to conceptually say, okay, this is what's going on in real life. Trust me, because when you build that bridge, boy, you better know what's going on. You better watch those significant figures too. You can't round a measurement. Oh, Lord, and I have kids. I've taught 28 years, and I'm 29th year of teaching. And I've always had a few students, not many, but a few, that always want to round a measurement, round a measurement, round a measurement. You don't round measurements. You can't. You round a calculation based on your significant figures, the precision of your device, okay, based on that. But you never round a measurement. By cracky, if you put a meter stick on there and it's laid out in millimeters, and you get, I don't know, you get 115 millimeters, or it falls in between 115 and 116, then you better say 115.5. You are allowed to estimate, okay, but you don't just, oh, to heck with it, 116 or 120. You don't round measurements. You never round a measurement, okay? Okay, that is so important. Please do not forget that. Okay, next one. Basic kinematics. The figure shows the velocity of a particle as it travels along the x-axis. What is the direction of the acceleration at t is equal to 5 seconds? I think that's supposed to be an equal sign. Yeah, it is. For whatever reason, when I put this thing in here, the symbols don't show up too well. That's supposed to be not -5. That's supposed to be t is equal to 0.5 seconds, okay? I know it looks like a negative. It's not negative. So at 0.5 seconds, it says what is the direction, and where is that at? That's, well, here's 1 second, so that's what? That's about right there, isn't it? It's real close. Okay. All right, y'all. What is the direction of the acceleration? Because notice this is velocity versus time. This is velocity versus time in meters per second. Anybody want to take a stab at it? All right, if I were to take the slope of this line from there to there, what am I going to get?
A negative slope.
Very good, a negative slope. So it would have to be going in the what?
Negative direction.
Negative x direction. Very good. So it would have to be that answer right there, in the negative x direction. Very good. That's exactly right. Think about it physically, what's going on. In other words, the object is doing this right here. It's going along, and it's slowing down, and then it's going to turn around and come back. Okay? This tells me the velocity is slowing down, so that means the acceleration has to be in that direction. It has to be. Come on, guys, when you hit the brake on your car, it has to be in the opposite direction, or else you do not slow down and eventually stop. I mean, that's just common sense, guys. You don't need a PhD to understand that. That's just common sense. All right. Any questions? I think we have one more. Yeah. Last one. I love these now. And I spent some time picking these out yesterday. And I tried to get some. Matter of fact, I kind of tweaked a few of these a little bit. I think I tweaked one or maybe two. I know this is one of the ones I tweaked because the answer they had in the test bank file was incorrect. You do find some of those every now and then. All right, free fall. Which of the following position versus time graphs would represent an object thrown upward? Now, in other words, I'm standing down here and I'm going to throw it vertically upward. I didn't say vertically, but I'm going to throw an object vertically upward, and of course it's going to come back and hit the ground, right? So which one of these, now notice it's position versus time, and it is in the y direction because it's straight up. You see the y there. This is y, and that's time, and this is y. I don't know how well y'all can see that. Okay, and that's time. Which one of these is going to be the most accurate?
C.
D.
Okay, some say C and some say D.
D.
Okay, we had another D. All right, anyone else?
C.
C. We got two C. We got three C's and two D's. Okay.
D.
D. All right. So we're tied up. Okay. Anyone else? Okay. Well, let's analyze it. When I throw an object straight up, what is that object doing as it's moving towards its maximum height? Is it speeding up or slowing down?
Slowing down.
Slowing down, okay. And its velocity is slowing down, and if its velocity is slowing down, and eventually, what is the velocity of the object, of course, at maximum height? That's a no-brainer, right? What is it?
0.
0 in the y direction, right? We're all looking at y, all right? Very good. So if its velocity is slowing down, what is happening to its displacement? Is it increasing? Is it constant, or is it decreasing? Increasing, constant, or decreasing? The amount of displacement that is occurring every second, is it constant, or is it decreasing till it reaches maximum height?
Decreasing.
Very good, decreasing. So would this show me a decreasing displacement?
No.
No, that shows a constant displacement, doesn't it? Okay. Does everyone see why? So which one would it be, folks?
D.
It'd have to be D. And again, you say, well, now, Mr. Shields, I thought gravity is constant. You are exactly right. You are exactly right. But you've got to, this is where I told you here a while back. And again, y'all are participating, and I really appreciate it. Y'all are thinking, and that's how we learn, okay? And I'm going to try to do more of this. I really am, okay? But you got to remember what you're plotting. You're plotting displacement versus time, okay? All right. Not velocity versus time. Not velocity versus time. All right. So it would have to be this one. This is showing that displacement is decreasing, decreasing, decreasing over the time interval till it finally flattens out. No more change in displacement. And then it starts going in the negative direction. Because we know that the velocity, once it starts to come down, the velocity is negative. Right? It's positive going up, negative coming down. Now, what if I were to say what would be the velocity versus time graph? What would it look like? Now, we did this in class the other day. I forget what page this is on. Yeah, page 52. We did this in class the other day. For an object thrown straight up, let's see, position versus time. Yeah, with an initial speed, thrown up with an initial speed. Let's say the initial speed right here, V initial, is 10 meters per second, okay? So what would my velocity versus time graph look like for an object thrown straight up and then it falls back to the ground?
It would look like graph A.
It would look a lot like A. Very good. Yeah, it would look something like that right there. It sure would. Very good. Because right from here to here, from here just before we hit 0, this is all positive velocity. Okay? But it's decreasing positive. Then once it turns around and starts coming down, then it's increasing negative velocity. Does that make sense?
Yes.
Okay. Very good. Very good. So again, guys, I want you to pay close attention to what the graph is showing you, and then think about it in the physical realm. Apply it in the physical realm. And see, you say, well, how's this conceptual? Well, guys, you got to understand gravity. And you got to understand that when you have an object in free fall, y'all, it is parabolic motion. All of you that are crazy about the quadratic, you're exactly right. That is a quadratic function right there. It's quadratic because we're plotting displacement versus time. However, when we look at velocity versus time, it's actually a linear relationship, okay? It's a linear relationship because the acceleration is constant. And when you plot acceleration versus time, then you're going to get, ooh, and I almost made a boo-boo. It's actually going to be down here because it's negative 9.8. I almost drew it up here. Okay, it's going to be negative 9.8. All the way up and all the way down because the gravity is continually pointing towards the ground, towards the center of the earth. Okay? All right, any questions? Now, does gravity change as you move in elevation? Well, sure it does. The old clockmakers, now I'm going to throw in a little teaching across the curriculum here. You say, well, why is this important? Why do I need to know this? Okie dokie. Let's say you're going somewhere and you don't have any digital access whatsoever, but you have an old pendulum clock, okay? And it's just, heaven forbid, you know, something happened to the power grid and there wasn't any power and you still wanted to keep accurate time. Could I do it with an old pendulum clock? You sure could. Now, the only problem you might run into is if someone had dinked with the length of the pendulum. And you could actually do some experimentation to determine if the length of the pendulum is off. You can actually do the simple pendulum experiment, and you can determine if the length of the pendulum is accurate or not. Okay. But the old clockmakers, if they sold clocks to people that lived in high elevations, they had to teach them, say, now look, the acceleration of gravity is not as much at a high elevation, so you have to adjust the length of the pendulum. You say, well, what is that equation? You probably did this in high school. T is equal to the square root is 2 pi. Let's see. The period would be equal to, Lord of mercy, I just went completely blank. 2 pi over, 2 pi times the square root of L over G. There we go, the length of the pendulum. 2 pi times the square root of L over G. And so you could calculate G for a given location. You could calculate the length of the pendulum too. If you knew G, you can calculate what the length of the pendulum does for it to, say, have a 1 second period. Okay, so that's a very useful, it's a simple experiment, but it's extremely useful. And y'all, I'm serious, the old clockmakers, when they built their clocks, you know, not everybody lived at sea level. And so they had to realize that they had to adjust the length of that pendulum based on where they were on the surface of the earth. So you had to have a little bit of physics knowledge back in the old days to make sure your clock kept good time. Okay? All right, didn't know if you knew that, but now you do. Okay, great. All right, I'm going to stop this video.